Hello again, everybody. This is Sylvain Rochon here with a little glimpse of the future leading to many opportunities for the bold who wish to change the world. Today, we'll be talking about quantum computers. And what's up with that now? Because, people have been talking about quantum computers since the 1980s or so. And just to explain what it is in a nutshell, usually computers are binary, ones and zeros using transistors. There's electricity that goes in, then it's a 1. If there's no electricity, it's a 0. So you have little logic gates, little tiny things now in our microchips that are flipping back and forth between ones and zeros. And that's how computers kind of work. You have all these ones and zeros kind of being flipped around. And going through the wires essentially, and on the microchips of your CPU, and the computer is computing X amount of calculations a second using, all sorts of techniques that's been developed for since the 1950s or so. But quantum computers essentially, again, we've been toying with it. It's essentially an ion. So instead of a physical gate that flips through voltages like on and off, like a switch, what it is it's an ion, an atomic ion. So it's a single atom that is kind of captured in a little tiny atomic box, if you will, and it changes its state, so it can create something similar to a 1 and 0. But because quantum computing is funky. It can have several superimposed states, so it can have like 4 different states or 6 different states, 8 different states instead of just two different states of like ones and zeros. So essentially, the capacity of a what they call a qubit, which is the quantum version of a transistor, is actually exponential. Instead of being additive or multiplying when you add transistors, then you're essentially adding more ones and zeros. So it's a binary system. So it's to the second power essentially when you're dealing with traditional computers. But with quantum computers, it's actually even more exponential than that. So you can do way more calculations a second potentially, and since it's an ion, the transistors, the qubits, are really, really small. So they can, be like super miniature compared to traditional computers, right? A lot smaller potentially. Now, the reason why we haven't been hearing a whole lot about quantum computing in application is because traditionally what we've been using to flip the state of a qubit, of the qubit ion from ones and zeros and whatever, we've been using lasers. So, which means if you have a whole bunch of qubits, you need a whole bunch of lasers focusing on individual atoms, and so that's not scalable. You can't put a lot of qubits together with all these lasers firing about. It's just unmanageable. It's a big problem. However, recently a team has been able to, I believe from Australia in this case, have been able to use voltage, which is the traditional way to flip a switch, to flip a transistor, to flip or change the states of qubits. So that brings the qubit essentially into traditional machines in some way. So it's way closer to us as far as feasibility. So now, and you can scale that because we know how to scale using voltage. We've been doing it since the 50s. So quantum computing as a reality of a computer, like a real computer using quantum computing, is maybe a year or two away experimentally. Well, actually, an application kind of coming out into the world, probably for industry at first and things like that. Now, the opportunity for you guys that are listening is, well, get into that. I mean, if you're into computing, you should look into quantum computings and qubits, and how to take those qubits out of the laboratory and using them into in the application, right? Because, like I mentioned before, these are super small. So ultimately, we can do real nanorobots with those. You can create robots technically because the potential power of computing is exponential, and they're really, really small, you can make robots that are like hard even to see, or maybe kind of invisible to the naked eye. So you can have nanobots that are crawling around, invisible to the eyes, cleaning, healing, repairing, building, doing all this stuff, and they're self-repairing themselves, and they reproduce themselves when they're missing a few bits, because some of them may come into disrepair or get damaged or lose power, whatever. So you can have a situation where a little bit like Star Trek, where everything is clean because you have all these nanorobots flying around. Now, those of you who don't like insects, maybe you're reacting to this, but just to let you know, you have a whole bunch of insects running around you that you don't see because they're just that size, and they're doing a bang-up job with our bodies, with our follicles, and with our fat, and they're processing all throughout our skin and our bodies, all this stuff that needs to happen biologically, but you can't see them, but you're crawling with insects. Now, if you know you're crawling with insects and you've lived X amount of years crawling with insects that are doing their jobs and it doesn't really harm you at all, in fact, they're protecting you, why not being crawling with nanobots that do jobs that we can program them to do? That could be super exciting, right? So these are some of the opportunities that are ahead. Until we get to the real interesting bits, well, we need to do something a little bit more scaled down, perhaps monitoring systems that can flow into the bloodstream that are way smaller and that can do a lot more than just measuring glucose levels, for example, for diabetics. Because that's been done already. But you can imagine all the sensing that can be done, sending information out. You can call an ambulance at a distance when a person is in any kind of distress, for example. And it's all the little nanobots that are invisible in a person's blood that does that, where the biological body can't do that, right? So everything is possible with that, with miniaturization as well as exponential computer power. I've been talking about Moore's law. Well, quantum computers can potentially increase the boundaries of that, push those boundaries, and bring super intelligent, conscious AIs to bear, or high-performance data crunching computers that can calculate pretty much anything that goes on in the world within a second, and give us predictions on the weather, climate change, whatever else we need. This is the computing power that we are dreaming about. So let's work towards that. Let's encourage those laboratories that are working with quantum computing, and let's develop those applications that will change the world. Anyway, that's it for now. If you want more helpful insights on how to benefit from changing the world into a better place, please comment below. Let me know what you need. Share, and of course, subscribe to the channel. That's super helpful to me. Now, I'll see you next time, and in the future of today. Ciao for now.